thank you so much for the invitation to this conference. I'm very excited because this is actually exactly the topic of my research, motifs in representation theory. So I'm very happy for the next week. Okay, so before I start with my actual talk, I want to give an overview of certain applications of motifs in geometric representation theory I have come across so far. Yeah? It's not a complete list, it's only the stuff I know personally, just to maybe get an overview of stuff that is happening. So the starting point is the following. In the last decades of motivic homotopy theory, I guess there was a lot of development and lots of interesting definitions, theorems, and constructions one can use. And in geometric representation theory, or in the past of geometric representation theory, people have been using all kinds of interesting constructions from, let's say, algebraic geometry anyway, so this is just a new set of stuff we can use. Okay, so now I want to go through potential different things that one could do with those new categories of motifs that have been constructed. So one big idea is the following, that you would say, so in geometric representation theory, one would often work with constructible sheaves on manifolds, or algebraic incarnations of those categories, like for example, L-adic sheaves or D-modules, or even better, they are kind of mixed upgrades of those algebraic categories. So they are mixed L-adic sheaves, also called Weyl sheaves, or they are so-called mixed Hodge modules, which are even stronger than those other algebraic analogs. So now, similarly to what has been happening in Shane's talk, one can say, okay, really all of those different algebraic mixed sheaves, they should come from underlying motifs. And so the idea is to, instead of using those kind of mixed sheaves, as has been done before in geometric representation theory, one makes use of motivic sheaves, so this category DM. And the hope would be is that the other mixed sheaves that people have been using before have been very successful. Yeah, I mean, they're important because you can use them to prove the decomposition theorem. From this you follow the Kaštan-Lustig conjectures. Or in Baileyson-Ginsburg's Koszul duality for flag varieties, they play a central role. So now let's try and do the same thing with DM. And so here we immediately get two advantages. One advantage that some people are interested in is that everything is independent of the auxiliary prime number L maybe, because if you do L-adic sheaves you always have this L floating around, but which L do you choose? Yeah? So this would be one point. And there's also another technical advantage that sometimes it's even easier to work with the motifs than with the usual mixed categories, because in certain situations there are no extensions between Tate motifs. If you do it the right way, you do base in characteristic P and coefficients in Q, for example. Okay, so this would be two potential advantages. So this idea has kind of been pioneered by Zörgel and Wendt, who kind of revisited the whole story of perverse sheaves on flag varieties using this theory of motifs, and showed that the motifs give a technically cleaner language and a very nice picture that you have a Koszul duality between motifs on flag varieties. Okay, and then there's also the work of Richards and Schollbach, who apply, I mean, I hope I'm not saying anything wrong, who applied this in the geometric Langlands program. And I guess one question here would also be, would exactly be an independence of L questions. There's a conjecture of Laforgue on some kind of independence of L, which they hope to prove with motifs as well. Yeah?
We hope that, yeah.
Okay, good. And yeah, okay. So today it will be more like a smaller thing, yeah? More like a toy theory which I want to present, which kind of puts together motifs and geometric representation theory very directly in a nice way, which is something called Springer theory, and we want to do Springer theory motivically. I will talk about this in a second. Okay, so this is one direction. Use the M instead of all of those mixed sheaves that have been around before. Another direction is the following. So the mixed sheaves that I talked about before, like the mixed L-adic sheaves or the mixed Hodge modules, they only work with characteristic zero coefficients. I mean, that's kind of built in. So, but the dm, or you can define variants of dm, which also work with characteristic p coefficients. So here you could hope that you can use motivic sheaves to construct in a geometric way mixed sheaves in characteristic p, and then you can hope to apply this in modular geometric representation theory, where such categories would be needed. And that's a joint project where I was working with, or I am working together with Shane Kelly to kind of try to pursue this idea. Okay? And then a last idea, and maybe this ties into the first talk, is the following. I mean, dm, if you, in these constructions of motivic categories, dm is just one possible thing you can construct. You can also use more exotic, you can construct more exotic categories of motifs, which are tied to other cohomology theories, yeah? So for example, you could say, I'm interested in K-theory, and lots of people in geometric representation theory are interested in K-theory. It's a very fundamental object. So you could say, okay, instead of studying the usual motifs, I consider K-motifs which compute K-theory, or homotopy invariant K-theory. Okay, and then the idea is that the K-motifs, they should also be important in geometric representation theory, and they should be kind of Koszul dual to the usual constructible sheaves on manifolds, yeah? So this would be another thing that motifs bring for you, and you can think of other generalized cohomology theories, motivic cohomology theories, that you can plug in here, and suddenly you get new categories which behave similarly to constructible sheaves on topological spaces, but they are associated to a different cohomology theory, which can be useful, yeah? So, and this also pursued in the context of Koszul duality. And now the most important point is, this is only the stuff I know. I want to learn about millions of new possible applications in this week, yeah? Let's see. Okay, good. So now let's start with the talk. So the plan is the following. So I think a central concept which happens to both people in geometric representation theory and motifs is the concept of convolution of cycles, yeah? Which is a generalization of composition of functions, yeah? So I want to start talking about this elementary concept of convolution. Then I want to talk about dm, and then next I want to introduce some kind of tool from homological algebra called Weyl structures, which is kind of dual to T structures, and it has, I think, it has not been, it's not so well known in representation theory. Some motivic people know it because they work with the weights of motifs, but I want to argue that it's actually very fun and good tool to work with, very similarly to T structures. And then for the rest of my talk, I go into some results where I put all of this stuff together in the context of Springer theory. Okay, so then let's start. So all varieties are over Fp bar, and all the spaces are also varieties in some sense. You need adjectives always for the motifs, yeah? You need quasi-projective varieties sometimes, and so on, yeah? I won't talk about those adjectives at all. And all coefficients are rational, which makes everything much easier as well. Okay, so let's talk about convolution of cycles. Let's say we have this following basic situation. We have three smooth varieties over our base field K, X, Y, and Z. And then I have three proper maps as well to some variety S, and this doesn't need to be smooth anymore, yeah? So that's the basic setup. So now, what can I do? I can form the fiber product, or lots of fiber products of those varieties. X with Y, Y with Z, X with Z, yeah? So I get lots of spaces, namely those fiber products. And then I can look at the Chow groups of cycles or co-cycles on those fiber products, okay? So one way to think about it is to think about those Chow groups, I mean if they're in the right dimension, to think about them as correspondences from X to Z, to X to Y, or between those two spaces. Okay, so the cool thing about this is that now actually I can define a convolution product on those spaces. Yeah? So here let's say I start with a pair of cycles on X times Y and Y times Z. Then I can make them into a cycle on X times Z. Okay? Just using the usual functorialities, push this through all the functorialities, and then you get a cycle in X times Z, yeah? And this is kind of, this convolution is a generalization of composition of functions, yeah? You take the graph of functions and the cycle associated to this convolution corresponds to the composition of functions, but this is more general. And in fact, it doesn't only work with Chow groups. I mean, this is just because we work with motifs. I wrote Chow groups here. But with any Borel-Moore type homology theory, like usual Borel-Moore homology on your complex manifold, or K-theory, and it also works equivariantly, yeah? So you just need the right functors to write down this formula. Okay, good. So now, how does convolution appear in geometric representation theory? And so there's this book that probably everyone has who does geometric representation theory, the Chris Ginsberg book on representation theory and complex geometry. And here they, they do lots of convolution, let's say. And let me give an example of what you could do. So let's say S is the nilpotent cone, so N the nilpotent cone, which is just a set of all n times n matrices that are nilpotent. Okay? So that's usually a singular variety, yeah? Okay? So the more Jordan blocks you have as a matrix, the deeper you are in the singular locus, let's say, yeah? The zero matrix is at the most singular point of this variety. So that's the nilpotent cone. And this has a nice resolution called the Springer resolution, which is a resolution of singularities. So what you do here is you take your nilpotent matrix and you add some extra datum, namely a flag of vector spaces that is preserved by this nilpotent operator. Okay? So this is basically a resolution of singularity. So if you have just one Jordan block, your operator is just one Jordan block, there's just one flag that is fixed by this, this operator. So for all the matrices with one Jordan block, which is the generic case, this is an isomorphism, the Springer resolution. So that's good to make it a resolution of singularities. And then some very interesting phenomenon happen over matrices that have more than one Jordan block. Then the fibers of this resolution can be extremely interesting. Okay. So let's do easiest example. Let's say n is equal to 2, the nilpotent cone. The real points really look like a cone with just one singularity at the zero matrix. And you have the blow up of this is exactly the Springer resolution, which can also be identified with the cotangent bundle of the projective line. Okay. Good. So now let's see how we can use this in representation theory. So now let's say we form this the fiber product of the Springer resolution with itself. So we get a new space. This is usually called the Steinberg variety, but let's not worry about this. So then you can look at the Chow groups of this. So now I looked at the Chow groups of top-dimensional cycles, or dimension 0 co-cycles. So basically at the vector space of irreducible components of this fiber product. And it turns out this fiber product has n factorial many irreducible components. And even better, if you equip this Chow group with the convolution product, you get the group algebra of the symmetric group. Okay? So this is a geometric realization of the symmetric group in terms of this convolution algebra you can get with the Chow groups. Okay, yeah? And even better, you don't only get the symmetric group, but you get the natural convolution action on the Chow groups of the Springer fibers, so the fibers of the Springer resolution. And there are also as many of them as conjugacy classes in the different ones, as conjugacy classes in the symmetric group. And so you get all the irreducible representations as well, like this. Okay? And in the, here I did the example n equals 2. Okay, that's not so very, very interesting, yeah? The S2 group is not, yeah. Okay, but still, yeah. Okay, good. And this is just the starting point of lots of other things. So everything is named after Springer in this kind of thing because he was the first one who came up with this construction of the representations of the symmetric group in this geometric fashion. And also he not only did it for symmetric group, but all Y groups. Yeah? They need to be a little bit more careful, but it's basically the same story. Good. And then there are many other algebras which you can also build like this. So for example, Lustig explained how to build the affine or graded affine Hecke algebra, which uses the same setup, but you use K-theory instead for the affine Hecke algebra. Then also some modern kinds of algebra like KLR algebras can also be built in this kind of, as this kind of convolution algebras on different spaces then. And also quiver Schur algebras and many, many more examples of interesting algebras in representation theory arise in this convolution setup. Okay, and so I want to call all of these situations Springer theory, yeah? Because they come from this basic idea, from this starting point of Springer. Okay, so now this is convolution in geometric representation theory. Let's see where convolution happens for motifs, yeah? And we've already seen this a little bit in Shane's talk. Namely, I mean, usually it's very difficult. You saw the different viewpoints on motifs in Shane's talk, and it's often, I mean, let's say for me at least, very difficult to understand the definitions of those categories of motifs, yeah? But actually, I mean, there's a very simple category of motifs that everyone could build if you just understand your cohomology theory, like Chow groups, a little bit. So let's say I look at the following category of correspondences over S, where I say my objects, I call them mx, just symbol mx, for every variety x that is smooth and sits properly over S. Okay, so I want to look at this. These are the objects of my category, and morphisms are just exactly given by those Chow groups we've considered before, yeah? So like this correspondences. Good. And now this category, I mean, you have like kind of a direct sum on this category because you can take the disjoint union of two varieties. And now let's say, okay, I want not only direct sum, so not only an additive category, but an idempotent complete category. Then you can just do it, yeah? There's a process of adding images of idempotence to a category, yeah? Not problematic. It's exactly what Shane did. He had a variety plus a projector, yeah? Like a tuple. Very simple, idempotent completion. And so for example, you could look at the motif of P1. This would split into two pieces. One is the Q, the unit, and one is the Slevschatz motif L, yeah? Okay, good. And now there's one more thing you do. This is related to this effective versus non-effective, but don't worry about it. You can also tensor invert this Slevschatz motif, whatever. And then you get Chow motifs, okay? So Chow motifs are just very elementary built out of Chow groups themselves, okay? And for example, you have the motif of Pn. This just splits into n many pieces corresponding to the decomposition of Pn into a point, a line, and so on, yeah? Good. So these are Chow motifs. So now Chow motifs have one problem, I would say, is that they only work for the smooth varieties, which sits properly over this S, yeah? So as soon as you don't have something like this, there's no Chow motif associated to it, okay? And also this problem kind of is reflected in the fact that this category of Chow motifs is just additive category, okay? And so the Chow motifs, I want to call them the pure motifs. Pure because they are pure, because in the sense that they come from something smooth, projected, let's say, or here in this relative situation, from something smooth that is proper over S, pure. And pure should be contrasted against the word mixed, yeah? And mixed means, oops, that you also allow general X. I mean, with general, you also have to put some small adjectives in front of X, but not smooth and projected. Okay, and then actually there's this other category, DM, and now unfortunately there are different names for this. So sometimes people call this motivic sheaves, I would guess, or relative mixed motifs, or triangulated category of relative mixed motifs. And they contain motifs for all the varieties, not only the smooth ones. And so they're called mixed. Okay, good. So now there are many definitions. We've already seen one in Shane's talk using the étale sheaves, inverting the A1. But there are many other definitions, and I would say it's if you want to work with them, it's easiest to just look at their properties instead of really knowing how they are defined. So in particular for any S, I get this kind of category DM of S. Yeah? It's tensor triangulated Q linear category. There's also infinity version of this, but whatever, we just do triangulated categories. And most importantly, those categories, they don't live like in a vacuum, but they are connected to each other. If you have a morphism of varieties, you get functorialities between them. Yeah, the usual push forward and pullback functors and their exceptional versions. And then very similarly to constructible sheaves on manifolds, you get something like localization triangles, base change formula, projection formula. There's one difference, huge difference I would say, to just the constructible sheaves on manifolds, which you encounter very quickly, is you kind of have to differentiate the Tate twists. You have to be careful with the Tate twists. Yeah? Maybe, I mean, if you don't work with motifs, you are used to Tate twists because they tell you something about the action of a Frobenius or the weights of your Hodge structure. But here there also appears. It must appear because the motifs are kind of universal. And so this is the Tate twist, which is an autoequivalence. And in this context of geometric representation theory, one often thinks of this as just a shift of grading functor in a way. Yeah? So that's a very useful analogy. Yeah? If you have a category of graded modules, you can shift the grading, and this maybe sometimes acts in a similar fashion. Good. And you have realization functors which bring you back from motifs to just the usual L-adic sheaves. And as Shane already explained, the motifs, they compute the higher Chow groups. So higher Chow groups, I mean, there are Chow groups, which you can just define using algebraic cycles. And the higher Chow groups are to usual Chow groups as higher algebraic K-theory is to K-theory, yeah? Okay. So, but, I mean, that's this. And if you just say S is just the base field, then this is the usual Bowodzki's triangulated category of mixed motifs, yeah? But here, actually, you don't need to put in a field. You can put any relative, any base, S. Good. And so this is now the first thing is that why is this DM a triangulated category if one would usually expect in a abelian category? The problem is, this is this problem with motivic T structures. So conjecturally there should be a T structure on this triangulated category. It cuts out an abelian category of mixed motifs and has nice properties, but this is related to the standard conjectures, yeah? So this will never be proven, so but it's still an interesting thing to know that kind of, if there would be enough algebraic cycles, then actually there will be a abelian category of mixed motifs. But, and this is why I will argue for the weight structures, there's something different than a T structure, which does exist. Namely, the Chow motifs, they are contained in DM as the motifs of smooth stuff which sits properly over S. And they are kind of the weight zero objects, or the heart of a weight structure on this category. Yeah? So you already see the difference between weight structure and T structure. The Chow motifs are not in the abelian category, but just additive category. And this is what happens with weight structures. But I will talk about this now. Okay, so let me talk about some concept from homological algebra for a second. So
Jens, can I interrupt you for a second?
Example, I have a nice abelian category with enough projective objects. Then I can look at the derived category of A, bounded derived category of A, let's say. So this is the same as the bounded homotopic category of projectives. Okay, this way you can just build this category directly. Good. So now let's say I have this triangulated category and I want back A. Then I can define look at the standard T structure, and the heart of the standard T structure is A again. Okay? So, but in the same way as a derived category has a natural T structure, a homotopic category of chain complexes has a natural weight structure, which I will explain in a second. And, okay, sorry. So these are the axioms of T structure, okay, whatever. And the heart of a weight, so on the homotopic category you can define a weight structure, which is kind of very similar, but it will cut out the additive category you started with, in this case projectives of A. Yeah? So this triangulated category here has a T structure which gives A as the heart, and a weight structure which gives the projectives in A as a heart. Okay? So the axioms of a weight structure are actually very similar to the axioms of a T structure, just you change around some numbers, yeah? Flip them around. Okay? So you have a similar orthogonality condition, but now it goes in the other direction, and you have a similar decomposition of your objects as distinguished triangles, but also you flip the indices around, okay? And so weight structures are very classic, T structures are very classical, defined in BBD, and weight structures are more new, I would say, and they were defined by Bondaco in the context of motifs. But you can use them wherever, yeah? You don't need, you can apply them to any triangulated category. Okay, so very similar axioms, but different outcome. Okay, so two important functors for weight structures and T structures are the following. Like when you have a T structures, there's Beilinsen's realization functor, which goes from the derived category of the heart to your original category. For weight structures, you have functor, but of course it's in the other direction, namely this is Bondaco's weight complex functor. It takes an element in your triangulated category and makes it into a complex of weight zero objects. Yeah? So this is Bondaco's weight complex functors. Both are not equivalences in general, but still very interesting to have. Yeah? Okay. And the last thing I want to explain about weight structures is how you can define them. So let's say you have a triangulated idempotent complete category, and you have some collection of objects inside of this category. And now let's impose some some conditions. We want that those objects are negative. So negative means that they have no positive extensions. So when I take object x, y in this collection of objects, and this hom from x to y shifted by n, it should be 0 if n is bigger than 0. No positive extension, so they are negative. Okay. And also let's say that T generates C as a triangulated category. Good. So then actually there's a weight structure on your category such that the heart of this weight structure is generated by T. So namely you take all objects in T, you take all finite direct sums thereof, all objects isomorphic to those finite direct sums, and also direct summends. So this will always, the heart of a weight structure will always be idempotent complete. Good. So you can actually prescribe the heart of a weight structure on a category like this, whenever you have a family of objects like this. And so then you can look at the weight complex functor, which goes from your category C to the homotopy category of weight 0 objects. And actually this is sometimes an equivalence, or let's say it's an equivalence if and only if the objects in T also don't have any negative extensions. Yeah? So then you call this family of objects tilting. So it's a very nice family of objects which is tilting. They just have homomorphisms between them, but as soon as you shift them away, no homomorphisms anymore. Yeah? Very special kind of family you can sometimes find inside of a triangulated category. So then the weight complex functor is equivalence, which means that your original triangulated category is just a homotopy category of an additive category. Very simple, yeah? Good. Okay, so let's look at examples of weight structures in representation theory and in the theory of motifs. So in representation theory, there's some very interesting phenomenon called Koszul duality, which works like this. Let's say you have a graded algebra, and you assume that the zeros part of the grading is semi-simple. So it's just a direct sum of simple modules in degree 0. Okay? And so for example, A could be a polynomial ring, yeah? Then in the grade 0 part, it's just K, the field, is simple, yeah? So this is semi-simple, the zeros part. And also you want the algebra, the negative part, to vanish. Okay, that's the start.
So it's semi-simple over A?
Yeah. Semi-simple. No, it's safe. It's semi-simple. It's safe.
Over A.
Okay,
over
sorry.
A,
I should write. Sorry. This is a mistake. I should have written A modulo A bigger than 0 is semi-simple.
Semi-simple A module.
Yeah. So just as a vector space A0, but as a module, whenever you multiply with something of degree bigger than 1, it should vanish. Yeah, sorry. This is just stupid. Thank you. Okay, perfect. So now you can look at all of those simple modules, so the direct summands of the semi-simple thing. And now you can look at the following collection of objects. Namely, you look at your simple modules and you shift them around. But you do it in a diagonal way. Namely, you shift them in the grading degree and the cohomological degree. Inside, this all happens inside of the derived category of graded A modules. And now, by definition, this algebra A is called Koszul when this family T has this tilting property. So when there are no extensions, non-trivial extensions between those diagonal objects. Okay? So this is all, the original Koszul duality is all in Baylis and Ginsburg-Zörgel Koszul duality paper. But that's just directly written out, the Koszulity condition, but not in terms of this term tilting. Okay. But it's the same thing. So in this setup, you can consider the following algebra, which kind of knows everything about this family T. Yeah? Namely, it computes basically all the homomorphisms between elements in T. But written out in terms of X, it looks like this. So this is called the Koszul dual algebra to A. It's another graded algebra. And you put the shriek, yeah? So kind of, you have A and you have the Koszul dual of A, which is this A shriek. And so now let's see what we can do. So this family T defines a weight structure. The heart of this weight structure is exactly everything generated by this A0 and its diagonal shifts with respect to grading and cohomological shift. And so we have the weight complex functor into the heart of this weight structure. And this is an equivalence because this family T was tilting. So now we can rewrite this homotopy category. Namely, it's just the same thing as the perfect derived category of graded modules of this A shriek. Yeah? Just the same thing, written in a different way. And now under technical conditions, which I won't go in here, this is just the bounded derived category of graded A shriek modules. So this whole functors here, this chain of functors, this is Koszul duality. It takes, it gives a derived equivalence between two potentially very different algebras. For example, if A would be a polynomial ring, then Schrieg, the Koszul dual, would be an exterior algebra. Yeah? So if a derived equivalence between polynomial and exterior algebra. And this is just using weight structures to write this down. Okay? But it's a classical thing. But I just wanted to say this is how you can use weight structures, for example, and the weight complex functor. Okay. Yeah, remarkable about the Koszul duality that it maps symbol modules on the left-hand side to projectives on the other. Yeah? So it basically flips around everything. Yeah, good. Okay, so let's see how weight structures work for motifs. So here with motifs, you are kind of lucky. The chow motifs inside of the category of all the motifs is negative. So you can use them to define a weight structure. So unfortunately, the chow motifs don't generate all the motifs, but only the motifs of geometric origin. But let's not worry about this. I don't understand it either. So the chow motifs are the heart of a weight structures on the category of motifs. They are the weight zero, the pure objects inside of the category of the motifs. And in particular, we get the weight complex functor. And I think the weight complex functor does something really cool here, because on the left-hand side, I have the category of motifs with its very complicated definitions. On the right-hand side, I just have the homotopy category of chow motifs. I explained to you how you can define chow motifs, so you also know how to look at the homotopy category of chow motifs. Yeah? So kind of one can think of this, I mean, this is not an equivalence, this weight complex functor, but the homotopy category of chow motifs is kind of a toy model of GM, I would say. Yeah? And the cool thing is that in many applications in the geometric representation theory, you don't want to look at all motifs, but just a subset of them. And sometimes for them, the weight complex functor is an equivalence. So you can really treat everything like you would be in the homotopy category of chow motifs. Okay, so this is how weight structures appear for motifs. And you should compare this to the following. So what the weight complex functor does, he takes a motif of something that could be singular potentially, or not proper over S, and it chops it up into pieces which are smooth and are proper over S. Yeah? So it basically decomposes the motif of something, so a mixed motif, which is why it's called mixed. It decomposes the motif into just pieces which behave like they would be smooth and proper over S. Yeah? And this should be compared to the classical philosophy of Deligne, that you have this philosophy of weights. Yeah? So you have the cohomology of something that is neither smooth or projective. Still, it has a filtration, and the different pieces of the filtration, they behave as something that is smooth and projective. Yeah? And this weight complex functor kind of reflects this idea. Yeah? That mixed stuff is built from pure stuff. Okay, good.
So when you say it can be an equivalence sometimes, what do you think?
So this is when you will see an example in a setting, but like when you only, I mean, the thing is the right-hand side of this equivalent of this here, the chow, the homotopy category of chow motifs, they can't see any higher chow groups because there are no extensions between the chow groups on the right hand, between the motifs of smooth projective varieties on the right-hand side. Just because they would live in different degrees in this homotopy category, they wouldn't interact at all. But on the left-hand side, there can be very interesting higher chow groups. So what this weight complex functor basically does is it kills all higher chow groups. In a way, yeah. So in a setup where you wouldn't have higher chow groups, for example, you have a base field Fp and you take rational coefficients, higher chow groups vanish. For this would be fine for this particular object, yeah. And everything glued from such object, it would also be fine. So for the mixed state motifs, for the stratified mixed state motifs defined by Zergel and Wendt, well, it would be fine. So restricted to this nice subcategories, it would be fine. Good. Yeah. Okay, but whenever you have higher chow groups or higher K theory, not fine at all. Yeah? Okay. Good. Then Motivic. Yeah, the topic of my talk, Motivic Springer theory. Okay, so now let's put everything together. So let's say, how much time do you have, by the way?
About 10 minutes, I guess.
Perfect. Okay, great. So now let's look at the following general setup, which often appears in this Springer theory setups, which I explained to before. So let's say now we also add a group into the mix, some linear algebraic group G. And now I have varieties. I want to call them Ni tilde. The N tilde in correspondence to the Springer resolution, yeah? But maybe I have more than one resolution. I have lots of spaces, Ni tilde. They are all smooth, and they sit properly over N. And also everything is G equivariant. G acts on all of those spaces. and the maps are G equivariant. Yeah, this is, for example, the case if you have the Springer resolution. Then G would be the GLN, or you can even add the GM or scaling factor as well if you want. Okay, good. And in this setup, you can form the following algebra. Let's call it E. Let's call it Motivic extension algebra. And you do the following. You check the Chow groups of all the pairwise fiber products of those spaces, Ni and J, yeah? A tilde. And also here, I mean, this is a small detail which I won't go into. You can also take G equivariant Chow groups, yeah? Okay. Which we do here, but don't worry about it. So G equivariant Chow groups. So this is an algebra, yeah? Because I have this convolution product, which makes it into an algebra. Okay, but now I have a different interpretation for this algebra, namely this algebra is also given by Hom groups in my category of motifs. Yeah? I explained that Hom groups in the category of motifs are given by Chow groups, and this is exactly how it is. But now, instead of using the usual DM, you use the equivariant version thereof. There's also equivariant motivic sheaves, and they have been built by Zörgel, Wirk, and Wendt, so usually use them. Okay? They're like equivariant sheaves, but equivariant motivic sheaves. Good. And now inside of the category of all motifs on this space N, we just look on the motifs we are interested in, namely the motifs which come from my Ni tildes, from my resolutions. So I look at the triangulated category generated by them, yeah? I mean, in DM, that's the same as when you look at all sheaves on let's say, topological space, too many, yeah? But we only want to look at them which really come from these resolutions. So this triangulated category here we call the category of Springer motifs. Okay? So we have this algebra, the motivic extension algebra, and this triangulated category of Springer motifs. Good. And now the result. So we put some assumptions on our resolutions. Namely, we want that the fibers of these resolutions are just Tate motifs. Yeah? So they kind of look like, the fibers can look like Pn. Yeah? So the fibers have nice motifs which are just the Lefschetz motifs, tensor products thereof or direct sums thereof. Yeah? So-called Tate motifs. And so this is one condition. And then there's another technical condition that there are only finitely many g-orbits on the images of those resolutions. Okay, don't worry about this. And then you can prove the following formality result. Namely then those Springer motifs, which is this complicated, a priori maybe complicated triangulated category of motifs, has a representation theoretic interpretation. Namely, it is just the perfect derived category of graded E modules over this motivic extension algebra. So on the left-hand side you have motifs, on the right-hand side representation theory, yeah? I mean, if you understand this algebra E, let's say. And this is, a statement like this is called a formality statement, and there are lots of formality statements in geometric representation theory. By formality, I mean, of course, you can write every nice category as modules over some algebra, but usually this algebra would need some higher structure. It can be DG algebra or A infinity, but by formality we mean it doesn't need to have any higher structure, but the algebra E is just the usual algebra, yeah? No higher structure, it's formal. So that's why it's called formality. Okay? Maybe. Good. And the proof,
sorry,
yeah.
one question about first condition. So it should hold for any x on M, or I just used it.
Ah, yeah, yeah, exactly. So whenever you have an x in N and you take the fiber under this pies, you get a space, like a Springer fiber, or I mean in the setup, whatever it's called. And this space should have a pure Tate motif. So for example, if this space has an affine stratification, which would be the case, for example, in the type A Springer theory, it's very nice. I mean, yeah, then this would be true.
Do you assume there is a stratification?
No.
There is
No, because
there is a constant sort of
there don't need to be such a stratification. Yeah, but just the motif needs to be pure Tate. It's a little bit weaker condition.
Yeah.
Just a little bit
That's
weaker.
what I was confused about.
Yes, but I will talk about this in 1 second. Yes, thank you. So the proof is actually very easy. So namely, you say, okay, I look at the family of all of those motifs of my spaces N tilde I, and actually this family of all of those motifs and their shifts is tilting. So there will be no extensions between them, and this is what you use the property PT and FO, which I've written down there, to show that there are no extensions in no directions. And also what's important here is that the base field, K, the higher Chow groups of the base field vanish. This is why we do everything over FP with Q coefficients, higher Chow groups vanish, else this wouldn't work. And then one just uses the weight complex functor, because this family T defines a weight structure, the weight complex functor, and this basically gives this equivalence. Okay, but this is very, let's say, general nonsense result, yeah? But let's put it to use in examples in geometric representation theory. So here, of course, one has to prove that in the correct setups, the assumptions of this theorem are fulfilled. The first setup is the following. Let's say you have the Springer resolution, and then you can look at the fibers of the Springer resolution. So in all the classical types, you can just, it has been shown that they have a affine stratification, so the motif will be Tate. Yeah? But in type E8 or E6, no, type E it's not shown. Yeah? There's just a paper of De Concini, Lustig, Borghesi, which show that in type A, the cohomology of those fibers behaves as if it would be as if it would have an affine stratification, and they do it with some. I mean, it's crazy, this paper. Yeah, they build a graph of many spaces, and all of those spaces are connected to each other by kind of blow-ups. But when you do blow-ups, you don't disturb the pure Tate property. And then they travel around until they get to some flag variety, which has an affine stratification. So they are fine there, yeah? So I just copied their proof, but put motifs instead of the cohomology everywhere, and it worked, yeah? I hope. Yeah, okay. Okay, the next thing is that also very interesting is the quiver, partial so-called quiver flag varieties, because they appear in this new stuff of KLR algebras. And I mean, you don't need to know what this is. So in type A, if you have a type A quiver, it's again affine stratification. It was known, and this was by result by Maximum. And in type A tilde, we proved, so for affine type A quiver with the cyclic orientation, we proved, so this is together with Catharina Stroppel, that those partial quiver flag varieties also admit an affine stratification, which makes their motif also pure Tate. Also, this means that we can apply this whole theory I explained to you before also in this setting. So now let's look at corollaries. First corollary, let's do the classical Springer theory on the nilpotent cone. There we can look at Springer motifs on the nilpotent cone. And there, this motivic extension algebra, I mean, it's just Lustig's graded affine Hecke algebra. It's a graded version of the affine Hecke algebra. Okay, so we get this equivalence of categories between those Springer motifs and representations of the graded derived category of graded representations of the graded affine Hecke algebra. Next example would be, we look at also the Springer setup are now for quiver representations. So we take a flag of quiver representations. This gives you spaces ni's, and you look at the motifs of them. And this basically now gives KLR algebras or quiver Schur algebras, which would be a different example from representation. Interesting algebras in representation theory, which can be linked to the motifs. Okay. So what are the future directions? So I explained to you before that you have this weight structure on the motifs, and the heart of the weight structure is the Chow motifs. Yeah, this has been proven. But the question here, and this can be found in a remark in Sorgel Work-Ben's paper, that actually does the same thing also work equivariantly. So this would be a question. The next thing is, which I'm very curious about, is the following. So the Lustig's graded affine Hecke algebra, it's a graded version of the affine Hecke algebra. And why is it graded? It is because it's defined using cohomology or Chow groups, which are kind of a graded, associated graded of K-theory. So if you use K-theory instead, you get the correct affine Hecke algebra, not the graded one. So as I said in the beginning, motifs, I mean, you can take different kind of cohomology theories. So maybe when you take K motifs, you should get the correct affine Hecke algebra. And I think this is really a point where the motifs get something that is impossible to do with the usual sheaves used in geometric representation theory, because they can't do the K theory this way. This would be another point. And then, of course, I think everything also should work with FP coefficients. So then you can actually prove some new formality results also in characteristic P. So with this, I have to talk to Shane more to get this equivariant setup also in characteristic P going. And I hope maybe that's inspiration for many new ideas which can come up like this. And I'm done with my talk. Thank you.